Our discussion for today is all about Introduction to Bridge Engineering. And this is your lecturer for today, Professor Danilo Guzman Jr., a registered civil engineer, a registered master plumber, a licensed professional teacher, and a graduate of Master of Arts in Education, major in mathematics. Let us now start our discussion. For the start of our discussion, let us have first the definition of bridge. What is then a bridge? A bridge is a structure providing passage over an obstacle without closing the way beneath. The required passage may be for a road, a railway, pedestrians, canal, or a pipeline. The obstacle to be crossed may be a river, a road, railway, or a valley. In other words, the bridge is a structure for carrying the road traffic or other moving loads over a depression or obstruction, such as channel, road, or railway. A bridge is an arrangement made to cross an obstacle in the form of a low ground or a stream or a river without closing the way beneath. Again, what is a bridge? According to Merriam-Webster Dictionary, the definition of bridge is this one. A bridge is a structure carrying a pathway or roadway over a depression or obstacle. According to American Society of State Highway and Transportation Officials, or ASTO, the definition of bridge is this one. A bridge is any structure having an opening and at less than 6,100 millimeter or 20 feet that forms part of highway or that over or under a highway. And take note of this, anything that is smaller is just a culvert under the roadway. Let us now have a little study knowledge about span length, wherein we can simply classify if a given structure is a bridge or a culvert. When the given span length of a given structure is greater than 6 meters, then we can classify it as a bridge. But when the span length is less than 6 meters, then it is a culvert. Then a bridge having a span length ranging from 6 meters to 30 meters is then considered to be a short span bridge. But if the span length is ranging from 30 to 100 meters, then we can call the bridge as a medium span bridge. Then we can call it as a long span bridge when its span length is greater than 100 meters. Let us now have the types of bridge by traffic, and these are the following. First, we have the highway bridge for cars and trucks. Then we also have the pedestrian bridge, good for pedestrians and bicycles. We also have the railway bridge, good for trains. We also have the transit guideway, but of course, we also have the other types. The following pictures shown below are examples of railway bridges for trains. Coming up next, we have the highway bridge for cars and trucks. And then we also have the pedestrian bridge. And as shown below is a good example of a pedestrian bridge. Let's now talk about the types of bridge by traffic position. Actually, we have three types, and here are the following. First, we have the deck type, followed by the through type, and then we have the hop through type. Regarding now about the deck type, under deck type, structural components are under the deck. And also, it is simply prepared by the drivers because they can clearly see the view. And with this deck type of bridge by traffic position, it requires space under the bridge. But of course, we also have the through type. And with this through type of bridge by traffic position, the following are its characteristics. First, structural components are above the deck, obstructed view, and it is not a problem for railway bridges. And then lastly, no structures under the bridge. We have the precast, cast in place, pretension, post-tension, prefabricated, rivet, bolted, welded, and etc. As shown in the picture, it is actually an example of pre-stress and precast and pretension type of bridge. And within this picture shown, it is actually an example of steel fabricated type of a bridge. Let us now proceed to the types of bridges by structure. And the following are the basic type based on structural form of bridges. And the following are arc, beam, cantilever, cable stay, suspension, and others. Now, let us study each type of bridge by structure. First in the list, we have the arc bridge. Arc bridges are one of the oldest types of bridges and have great natural strength. Instead of pushing straight down, the weight of an arc bridge is carried outward along the curve of the arc to support at its end. These supports, called the abutments, carry the load and keep the ends of the bridge from spreading out. As we can see in the figure, we can see the vertical loads from traffic acting at the roadway deck and of course the forces along the arc. As shown in this figure or this picture is actually a very good example of a arc bridge, followed by the beam or girder bridge, and it is actually the most basic type of bridge. And it typically consists of a beam simply supported on its side by a support and can be made continuous later. And it is also typically inexpensive to build. And as shown in the figure below, we can see the vertical loads from traffic acting at the roadway deck and also the beam action as well as the reaction forces. Again and still, under the beam or girder bridge, currently most of the beam bridges are precast or prefabricated. And most of them are also simply supported, and some of them are also made continuous on site. In this picture, it only shows that a beam or girder bridge may be simply supported, cantilever, or continuous. Let us have now the cantilever bridge. In a cantilever bridge, the roadway is constructed out from the pier in two directions at the same time so that the weight on both sides counterbalance each other. And also, notice the larger section of the support to resist the negative moments. As shown in the figure is also an example of a cantilever bridge. Let us now proceed to the truss bridge. All beams in a truss bridge are straight. Trusses are comprised of many small beams that together can support a large amount of weight and span great distance. And typically, span length is ranging from 40 meters up to 500 meters. As we can see in the figure now, the figure is more about the different parts of the truss bridge, also includes in here the label of its parts. But of course, among the different parts of the truss bridge, we have the floor beams, stringers, deck, sway bracing, struts, portal strut, and the lateral wind bracing. Coming up next, we have the suspension bridges. Suspension bridge needs to have a very strong main cables, and cables are anchored at the abutment. And as shown in the figure is a very good example of a suspension bridge. Coming up next, we also have cable stayed bridge. All the forces are transferred from the deck through the cables to the pylon, and the roadway deck can be a concrete box deck, steel box deck, or steel truss deck. And then we have movable bridges. A movable bridge is a bridge that moves to allow passage for boats or barges. And a movable bridge may be of a bascule type, a lip type, or a swing type. Now, among all those types we just mentioned, which type should I use? In order to choose, we have to consider the following. First, we have the span length, bridge length, beam spacing, material available, the site conditions, speed of construction, constructability, technology or equipment available, aesthetics, cost, and access for maintenance. Let us now have the cost versus span length. The span length may be influenced by the cost of superstructure and substructure. If the substructure cost is about 25% of total cost, shorter span is more cost effective. If the substructure cost is about 50% of total cost, longer spans are more economical. Speaking about access for maintenance, total cost is always equal to the initial cost plus the maintenance cost. And take note of this, bridge should be made easy to inspect and maintain. Maintenance costs may govern the selection of bridge. First, steel bridge needs a lot of maintenance in coastal regions. Second reason, concrete bridge usually require the least maintenance. And then when it comes to the beam spacing determines the number of girders actually. For large spacing, there will be fewer girder, deeper and heavier girder, reduced redundancy, thicker slab, while for the smaller spacing, there will be more girder, smaller girder, more redundancy, and thinner slab. Talking about the materials, of course, we need the steel, concrete, it may be cast in place or precast. Material choice depends on the cost of material at the bridge site, and of course, the shipping cost from fabricators. And for the speed of construction, like for example in urban areas, The construction of bridges may disrupt traffic. That is why we have to consider the following. Prefabricated or precast member are the only choice. Second one, substructure. Construction may disrupt traffic more than the superstructure erection. May consider longer spans. Talking about the site requirement. First question, is the bridge straight or curved? Of course, we have to consider the following. Precast girder cannot be curved. Segmental prestress can have slight curve or cast in plate. Second one, is shipping channel required? Third one, shipping of prefabricated pieces to site. And the number four is the temporary post work required? Can it be done with the site conditions? But of course, we also have to consider aesthetics. An ugly bridge, however safe, serviceable, and inexpensive, is not a good bridge after all. Long span bridge over a river can be a landmark, thus aesthetics should be an important factor. Bridge should blend with the environment, smooth transition between members, avoid unnecessary decorations. Bridge should have an appearance of adequate strength. Determinant of bridge appearance in order of importance. Since we're talking about aesthetics, then what does it mean? Aesthetics qualities result from the appropriate arrangement of visual design elements and are used to evaluate a visual composition. These design qualities are intangible. They are perceived qualities that arise from relationships of design elements. But of course, take note of this. We have the four C's of bridge aesthetics, and these are the following. First, we have the context, followed by comprehensive, cost, and constructability. Speaking of context, all projects from a simple creek bridge to the longest multi-span water crossing must first be considered with a view to the context in which it is located. Now, when do we say comprehensive? The designs that work best are those that take aesthetics into account right from start. Now, let's proceed to the cost. No discussion of design considerations can be conducted realistically without asking how much is it going to cost? How about constructability? No discussion of aesthetics is complete without considering constructability. In this figure, we can see the different bridge terminology, slab on girder bridge, and also as shown in the figure, we can easily see the difference between substructure and superstructure. Substructure includes the piers, the abutments, and the foundations, while superstructure comprises all the components of a bridge above the supports. In this figure, we can easily see the typical bridge components and the other bridge terminology. Also, in this figure, we can see here the different parts of the bridge and the different bridge terminology such as the railing, parapet, sidewalk, deck, traffic median, stringer, bearing, column cap, column, and of course we have the pile cap and the pile. Again, still under bridge terminology, slab on girder bridge, we have the following. For primary members, distribute loads longitudinally and are usually designed principally to resist flexure and shear. For secondary members, these are bracing between primary members designed to resist cross-sectional deformation of the superstructure frame and help distribute part of the vertical load between stringers. They are also used for the stability of the structure, during construction. Wearing surface is the portion of the deck cross-section which resists traffic wear. In some instances, this is a separate layer made of bituminous material, while in some other cases, it is an integral part of a concrete deck. The deck is the physical extension of the roadway across the obstruction to be bridged. The main function of the deck is to distribute loads transversely along the bridge cross-section. For the stringers, beam-type primary members are also called stringers or girders. The stringers could be steel wide flange stringers, steel plate girders, in example, steel plates welded together to form an I section, prestressed concrete, glued laminated timber, or some other type of beam. Abutments are earth-retaining structures which support the superstructure at the beginning and end of a bridge. The abutments establish the connection between the bridge superstructure and the embankments. They are also designed to support the loads due to the superstructure, which are transmitted through the bearings and to the pressures of the soil contained by the abutment. On the other hand, a wing wall is a side wall to the abutment, back wall, or stem designed to assist in confining earth behind the abutment. Let's now talk about the piers. Piers are structures which support the superstructure at intermediate points between the end supports. Like abutments, piers come in a variety of forms from an aesthetic standpoint. Piers are one of the most visible components of a bridge and can make the difference between a visually pleasing structure and an unattractive one. A pier can actually be a solid pier, column bent or open pier, or a cantilever pier or armored pier. Speaking of bearing, bearing is a structural device positioned between bridge superstructure and substructure, which transmit the vertical and horizontal loads of the superstructure to the substructure and accommodate movements between the superstructure and the substructure. When it comes to the role of bearing, its role are the following. First, to transmit load from superstructure to substructure. Second one, accommodate relative movement between superstructure and substructure. And then finally, we have the types of bearing. A bearing may be a fixed bearing or an expansion bearing. If it is a fixed bearing, definitely rotational movement only. But if it is an expansion bearing, it can be rotational or translational. We also have the rocker, pin, or roller bearing. Mostly used for steel beams, it can carry large loads, requires eye clearance, corrosion can be a problem, need regular inspections, and high maintenance costs. And then we also have elastomeric bearing, made up of natural or synthetic rubber, very flexible in shear but very stiff against volumetric change. Steel or fiberglass is typically used to reinforce the pad in alternative layers to prevent it from bulging under eye load, allowing it to resist higher loads. Can accommodate both rotational and translational movements through the deformation of pad. Finally, we have the elastomeric bridge bearings, and this is actually divided into two types. We have elastomeric bearing and lead rubber bearing. Including the figure are the different parts of the elastomeric bearing, and of course the lead rubber bearing. For the elastomeric bearing, we have the flange rubber, inner steel plate, protective rubber, and outer steel plate. Same as with the lead rubber bearing, it also consists of the flange rubber, inner steel plate, protective rubber, and of course outer steel plate. And that's all for our session, this lecture. Thank you very much, and God bless us all.